Okay, in this video we're going to work on Chapter 9, Sections 9.4 to 9.7. And Section 9.4 starts us out with solving algebra word problems with strip diagrams and with algebra. Okay, excuse me. So, here is the strip diagram. They are very, very helpful because it's very much a visual presentation of what the word problem is telling us. So it starts out saying the Browns are buying a TV that costs $1,300. After they make 4 equal payments, they still owe $400 on the TV. How much was each payment? Okay, so this entire fee is $1,300. This is the amount remaining, and they told you that these payments, there were 4 of them, and they were all equal. So 4 parts of this problem have to equal $1,300 minus $400, or $900. So you can then figure out what each part is by dividing by 4, since they told you the payments are equal. So if you figure out that each part is $225 by taking the 900, that was your result when you said 1,300 minus 400, and divide that by 4, you get equal payments of $225. So this is just a strip diagram. It's the bridge to algebra, but it's not using algebra yet. Algebra, by definition, is when you use variables to represent numbers. So the big difference is, for each of these equal boxes, you give them an equal variable. So they're all labeled X, and it's in dollars, so they put dollars there. Now, I probably wouldn't have put the dollars there, but that's okay. I would do that in the last step. So if X equals a number of dollars in one payment, then you have the same setup, but now instead of talking about 4 parts, you're saying you have a number sentence. So this is an equation. You're saying 4 parts, so 4 of some X, plus the $400 that's remaining equals the total cost of $1,300. So get all of your numbers on one side, and we do that by undoing the addition that's right there. And undoing addition is a subtraction. So then you have 4x equals 1,300 minus 400, which was 900. Divide both sides by 4 in order to isolate the x. You are also undoing the multiplication of 4 times x by division. So you can say that either way. So your x, just like last time on the other side with the strip diagram, is going to be 225. So what if we eliminated, so say you start out with a strip diagram, maybe say in 6th, 7th grade. 8th grade, you're starting to do this. This is 9th grade. No more figures, okay? So we just say, okay, x is going to be the number of payments, number of dollars in one payment. Then 4 payments are 4x. After 4 payments, the Browns still owe 1,300 minus 4x, which is 400. So here you have your equation. Now notice they don't have the dollar signs here, just like we didn't have the dollar signs here, and that's why I would not put the dollar signs there. Okay, so you can see they went through the steps, and they're getting the exact same answer. Okay, so you definitely want to know how to do this, because this is an important step. So the very bottom that you can't see says, effective way to bridge to the introduction of variables, the variable meaning the x. Strip diagrams represent quantities just like variables, and segments on a number line do. So key thing, same length, same amount. Greater length, greater amount. Now, do you see how they made this 400 bigger? They could have made that smaller because you don't really know what that is going to be. So if you solve the problem and then work backwards, you can then create your sketch. So don't worry about an unknown commodity like the 400. You don't know the size of that in relation to the other x's. You can assume it's going to be greater, but you can always go back and fix that after you solve the problem. So you have to do a little bit of reasoning in this. Okay, let's move on to the next page. Okay, so here I want you to try one of these problems. So let's set it up with a strip diagram. So it says a candy bowl contains 723 candies. Some of the candies are red and the rest are green. Okay, so that's nice. I have red and green. But now this is the important line. There are twice as many green candies as red candies. Okay, so that means that you're going to do a red, and then you're going to do a green that's really twice the red. How many red candies are in the candy bowl? So solve this problem in two ways, with the aid of a diagram and with an algebraic equation. Okay, so I'm going to use a diagram. This is going to be red up here. This is going to be green. And for right now, I'm going to put X's in all of my boxes. Okay, this whole thing has to equal 723. So since I have 3 X's, I'm going to say 3X equals 723 from my strip diagram that has algebra in it. Okay, and then I'm going to say X equals 723 divided by X. So X equals 241. So therefore, since my red is 1X, my red's going to equal 241, but my green, which is 2X, is going to be twice that. So that's going to be 482. It's a good idea to add these together and just make sure that you are indeed getting 723. Okay, so this is kind of a strip diagram using algebra. You could have just talked about parts and not put the X's in there. That would have been totally fine. Another way to do it is just with algebra. So using only algebra, I know I have 3 X's, since each of those little things are X, equals 723. So this is the first approach. And then X is 241. Since I know that red equals 1X equals 241, green equals 2X, so that's going to equal 482. Okay, so if I wanted to do a strip diagram without algebra, I would have just done this. I would have made that red and this green, and then I would have said 3 parts equal 723. So 1 part equals 241, and then I would divvy up 1 part to the red and 2 parts to the green. Okay, so that's 3 different ways you can attack that problem. Okay, let's go on to the bottom of this page on the next page. Okay, so we're talking about sequences here. Okay, sequences are very big in math because it's a good bridge to algebra. It has students identify patterns, and math is all about patterns. So a sequence, by definition, is a list of items occurring in a specified order. These items can be anything: numbers, letters, figures, objects, or movements. Different kinds of sequences are connected with different mathematical ideas and therefore provide different learning opportunities. Okay, as I said, patterns are very important in math. Okay, so there are many great class activities involving patterns. So you can see in this first one, you have shapes that repeat. So circle, triangle, circle, triangle, circle, triangle, circle, triangle. Okay, in the next one, you have 2 yellow, 1 red, 2 yellow, 1 red, 2 yellow, 1 red. In the third one, you have a more complicated pattern. So blue circle, green triangle, yellow square. Blue circle, green triangle, yellow square. And they've tied it in with letters of the alphabet. Okay, so you can kind of build on this many, many different ways. Okay, here you have growing sequences. So 1, 2, 3, 4, 5. It grows by 1 block each time. Okay, then you have 1, then you have 4, then you have 9. So what's happening here? Well, think about 1 as 1 square. This is 2 squared, and this is 3 squared. And then we have another pattern down below here with the stars. Okay, so there's many ways you can introduce patterns. So let's go on to the next page, and we'll talk about how we can do some reasoning with this. So how can we reason about repeating patterns? Okay, repeating patterns help us to understand the concept of a unit. So the unit is what repeats. So this is very important in understanding units of base 10, for example. So here is a unit. It consists of three figures. There are 3 boxes, 3 squares, and there is a color difference. So I've got 2 yellow and 1 red. That's a unit. Okay, here's another unit. Okay, so repeating patterns are made by repeating a unit. So you can have, students model this. They can make up their own patterns and show how they repeat. So we're going to do arithmetic sequences on the next page. Okay, so here, how can we reason about arithmetic sequences? So what's happening there? So here, with an arithmetic sequence, arithmetic means addition. So this is addition. Okay, it could be subtraction as well. There's a constant difference between the terms. That's what arithmetic means. So here, there's a constant difference of 2 here, a constant difference of positive 3, positive 5, a constant decrease of 1 here. All right, so that gives you an idea of sequences, and you can see how the patterns above show how you're jumping from term to term. Okay, every arithmetic sequence is described by a simple equation. This equation is related to the sequence in a special way. So, for example, if you're given this arithmetic sequence, the equation for this sequence is this. And you think, okay, how can that possibly be? So you've got to think about this in a special way. First, I want you to observe that the difference between the terms is 5. Okay? That is where this coefficient of the x comes from. The first term is 9. We need to find the term before that, which we're going to call the 0 term. So the 0 term must be 4. Now, how did I get that? Take your first term, subtract the common difference, and now you get the 0 term. So 4 is where this begins. So if x is 1, okay, if x is 1, then, so let's see, is this going to fit my pattern? So I have 5x plus 4. That 4 is the 0 term. Okay, can I get the first term? Well, let's see. Is it true that 9 equals 5 times if x tells you the term? Does that work? Yes. Okay, does 14 equal 5 times 2 plus 4? Yes, that works. Does 19 equals 5 times 3 plus 4? Yep. And we can continue one more. 24 is going to be 5 times 4 plus 4. Yep, and then we might as well finish out. 29 equals 5 times 5 times 5 plus 4. That checks. Okay, so very, very big point. The first term here is the first term, but you need the 0 term to start your equation. Okay, so subtract away your first term, because aren't you adding 5 each time? Well, figure out the number prior to the 9. That number is 4. 4 is your 0 term, and then the relationship between every subsequent term is 5 times the number of the term plus 4. Okay, so here we have illustrated this with a little table. Do you see how they got the 0th term? Okay, if you look, I guess the next page we'll look at the graphical analysis of it, but know that my equation, I'm just going to erase this a little bit, was 5x plus 4. Okay, let's go to the next page now. Okay, so our relationship was y equals 5x plus 4. So here are the points, and here is where the 4 is. Now the 4 is going to take on a special role. The 4 is the place where this discrete pattern is going to intersect the y-axis. So it's the y-axis intercept, which is usually just called the y-intercept. Okay, if I were to connect these points with a line, the slope of that line, the slant, the slope, would equal 5. So do you see that the coefficient to the x is the slope, and the 4 is the y-intercept? Okay, so that's kind of an advanced algebra analysis, but I just thought I'd put that out there. Okay, let's see if we can figure out this one together. So find the equation for the nth entry in the arithmetic sequence. Remember, 1 is the first term, so you will need to find the 0th term. Okay, so looking at this, I see a pattern that I am constantly adding plus 3. So the pattern is plus 3. So take, to get a 0 term, take the first term and subtract 3. That 0 term is a -2. To get the coefficient for the x, that's going to equal the difference between terms. So that is going to equal 3. Okay, so our equation is going to be y equals the 0 term plus 3 times x. And that's what you should be getting. Okay, so if you need to go back and go over that again, feel free, but that's the pattern that we're going for. Okay, so now we're going to go and talk about another pattern called a geometric sequence, and we're going to get that a little differently. Okay, so for geometric sequences, you either multiply or divide. Okay, so I have multiplication here, 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 and here's my division right there. Okay, so what's happening is you're jumping from term to term by either multiplication or division. So you're going to go up quicker and you're going to go down quicker than when you added and subtracted in the arithmetic sequence. Okay, so that's one thing. Okay, geometric sequences can be used in interest problems and growth and decay. Okay, so we're going to do this on the next page. Okay, so here is our situation. So you are generally given the 0th term. Okay, when they talk about decay or growth, that's your initial situation. So you do not have to work to find the initial term. That is usually given to you. Your job is to figure out what's the pattern beyond the initial. So what are you multiplying by? So that is the issue. So for this first problem, they are going to replace, we had an x before, they're going to use n this time. So for a geometric, y is going to equal your initial term is going to be right here, okay? And then you're going to multiply by whatever is being multiplied, which is 1.05, and you're going to raise that to the term. Okay, so n equals the number of the position. Okay, let's check this out. If I want the 0th term, that means we're going to take 1,000 times 1.05 to the 0. Anything raised to the 0 power is just 1. So my first term is 1,000. So that works. Okay, let's get our zeroth term is 1,000. Let's get our first term after one cycle of growth. Okay, so I take my 1,000, which is my starting position, and I say times 1.05 to the first. And when I do that, I should be getting 1050. And you can keep going and get every subsequent term that way. So how is this different from arithmetic? In two ways, right off the top of the bat. First, you are always given your 0th term. That is part of the equation. You can see it's your starting point. Second, you're going to grow by multiplication, so the operation will be multiplication, which is represented as a dot here, and not addition or subtraction. Okay, and the multiplier is here, and here is the number of the term. The number of the term is an exponent. It's the power. Okay, so let's see if we can figure this out. So looking at our problem, it says consider a geometric sequence whose first few entries are these numbers. Okay, this is my 0 term. 1, 2, 3, and so on. So find an equation relating an entry y to its position x and explain why your equation is valid. Okay, so y is going to equal, initial term is 0. How do they go up? Times 2. So times 2 and to the nth power. So let's figure this out. If I'm going to figure out the 0 term, 6 times 2 to the 0, 2 to the 0 is 1, that equals 6, that checks. Term number 1, 6 times 2 to the first, that equals 12, that checks. Term number 2, 6 times 2 to the squared equals 24, and they all check. So you may want to just go through that again so that you understand how I am getting an equation. And you should compare and contrast that with arithmetic sequences so that you know the difference. Okay, big takeaway, arithmetic, either addition or subtraction, geometric, either multiplication or division. In this situation, or in both of those situations, you are not given the initial number, the initial term in the arithmetic. You are given the initial term in the geometric. Okay, let's go on to the next page. Okay, so this next page is all about functions, and I think the top I had to cut off so I can get both of these diagrams in. So what it says in the top is a function is a rule that assigns one output to each allowable input. The set of inputs are called the domain, and the set of outputs is called the range. So this is a function machine. So here are your inputs. The inputs are the domain. You put them in the function machine. This machine doubled every number I put in. And your output is the range. Okay, the domain tends to be your x values and the range your y values. Okay, so this function, this machine, was a doubling function. Okay, this machine is a shape sequence function. Okay, so what's going to happen, input 1 gives you the yellow square, input 2 gives you the an output of the blue circle, and input 3 gives you the output of the green triangle. Okay, this machine gets repeated over and over and over again. So this sequence can be viewed as a function when you term your machine as doing these kind of things. Okay, let's go to the next page with this. Okay, when you have a function, you can represent it with a table and with graphs. So here's a table, Okay, so you have your input, which are your x's, and you have your output, which are your y's. Now, every x can only give you one y. That's the definition of a function. Okay, you cannot repeat your x's. You can repeat your y's. So here is your graph. And you can see that on the horizon, those are your x values. So the 0, the 1, 2, 3, 4. Okay, so they should have had another little dot right there at 0, 0. Here is your y. Okay, your y is your vertical axis. Your x is your horizontal axis. Okay, your x is your input. Your y is your output. Okay, and the graph is what results. So this is called a continuous function. I'm going to abbreviate function this way because you connect the dots. If you didn't connect the dots, the other type of function is a discrete function. And there you do not connect the dots. Okay? So I'm going to say dots only. Okay, let's go on to the next page. How do expressions and equations represent functions? So this says a variable that is used for the inputs of a function is often called an independent variable. And a variable that is used for the outputs of a function is then called a dependent variable. Okay, so this is how it works. This is your output. Okay, it depends on your input. Okay, your input doesn't depend on anybody. Your input is independent. Okay, so as I said earlier when I was talking about the table and the graphs, a function is a rule that assigns one output to each allowable input. Okay, so every x can only give one y. Okay, so that is the definition of a function. Okay, and let's talk about linear and other relationships on the next page. Okay, a linear function is a function whose graph lies on a line in a coordinate plane. Okay, so this is what we just did before. This is your slope, okay, of the line. This is your y-intercept. Okay, here's your y-intercept, and then the slope is the 5/3. Okay, linear functions have a slope, which is a rate of change, and a y-intercept. All exponents are 1, so that means x is not raised to a power. Okay, there are many other functions. Okay, by contrast, here a quadratic function does have one term raised to the second power. You have inversely proportional functions like this, and you have exponential functions. Now, there's an entire course devoted to algebra, so we're not going to go any further than that. But there are many different functions. One thing that's consistent is the y is always going to be your output. It is your dependent variable. Your x's are always going to be your inputs. They are your independent variable. Okay? So that's the end of this section, and that's the end of this course. So I hope this was helpful for you. I want you for this section to focus on the strip diagrams. They are important, and focus on the sequences. Be able to create an arithmetic and a geometric sequence.